So then I can really pick the right title here, review of the single level model. And we're switching to a different example, British election study data from 2001. In particular, I'm interested in this dependent variable, whether someone voted for Labour in the 2001 election or for another party. So I have a 0-1 coded dependent variable, 1 if the person voted for Labour, 0 if they didn't. And there are basically 3 kinds of explanatory variables that I'm exploring here. Again, I did not put that much thought into the specification, but one predictor here is whether someone identifies with Labour as a party. One is the ideological distance to Labour, and then I have class as a predictor as well. The quantity of interest in these models is actually not the 0-1 for Y, because that 0-1 coding on a nominal scale like we have here is essentially arbitrary. What we're actually trying to predict is the probability of a Labour vote, and we call that pi sub I. That's the probability that some individual I votes for the Labour Party. Now, there's sort of 2 ways to introduce this model. One is to use the terminology of generalized linear models. And normally I would skip this, except that the machinery that we will use instead of to estimate these models uses this language of the generalized linear models. So here is sort of the things that we need to actually wrap our brains around this. We have our dependent variable, and it has a distribution, which in this case is the binomial distribution. Strictly speaking, it's a Bernoulli distribution, but the Bernoulli is just a special case of the binomial. Then, that's something we need to know, because when we get to the machinery, we want you to specify the distribution. Secondly, we need to introduce this concept of the linear predictor. That's also something that comes out of the generalized linear modeling literature. The linear predictor is sometimes indicated by eta. Eta here is not a latent variable, as the way it was in the previous slide. Now it's just the linear predictor, which means it's a linear function of the predictors. Beta 0 plus beta 1, x1 plus beta 2, x2, etc. And what we now need to do is to link this linear predictor to the mean of the binomial variable. The mean of the binomial variable is pi. And how do we do this? We do this by way of the Logit link function. It turns out that, at least in the Logit model, this linear predictor is equal to the natural logarithm of the probability of voting for Labour over 1 minus the probability of voting for Labour. Or, we put this differently, the natural logarithm of the probability of voting for Labour over the probability of voting for another party. And that expression, ln pi over 1 minus pi, is known as the Logit. And the Logit is equal to this linear function here. Now, if we take the inverse of the Logit, in theta, that's literally what you would type, i.e. Logit, you end up with the predicted probability. So the predicted probability is the inverse of this thing which ends up being e raised to the power linear predictor over 1 plus e raised to the power linear predictor. This here is the so-called link function. This is another thing that you will need to specify when you do a multi-level logic model in STAIN. Now, that is one way to think about the model. I actually think that for some other purposes, it's actually sometimes more useful to think of this in terms of the latent variable model. When we adopt that idea, then we say, well, this 0-1 variable that reports whether someone voted for a label or not is in some ways a very crude reflection of an underlying continuum where we could measure with infinite precision what a person's propensity to vote for labor is. And that underlying continuum I call Y star, and it's unobserved. You don't know it. But you could at least imagine that there is such a thing. That sort of here you have negative infinity, those are the people that would rather be dead than ever be caught voting for labor. And then here are these people that even if labor were to start the Third World War, they would still want to vote for the party. You could imagine positioning people along that continuum. Now, that continuum we now model, and we model it by way of this linear predictor I introduced earlier. And then there's an error term, this epsilon I, which is random variation. Literally things that influence Y star, but that are not included in the linear predictor. And for this epsilon, I assume a standard logistic distribution, call that L here. Standard logistic means the two parameters of the logistic distribution are set to 0 and 1 respectively. Now, we need to link this latent variable specification to that what we actually have information on, which happens to be Y. We all know this Y star. And we will see that that has some implications in a moment. So how do we do that? Well, here is one way you can think about it. We say that Y takes the value 1 whenever this Y star is positive. You say, well, you have to at least have a positive inclination towards voting for labor in order to be voting for labor. And if you don't have that, you will score 0. In some ways, that 0 is a bit of an arbitrary cutoff point, but it isn't actually that relevant. We could have set it to anything, but if in reality the cutoff is not 0, but something smaller or something larger, that will be absorbed in the intercept in this model for Y star. So it's not that problem. Well, if we take this idea that Y is 1 and Y star exceeds 0, then we can model the probability of voting for labor as the probability that Y star exceeds 0, which, substituting this expression linear predictor plus epsilon for Y star, means that we want to know the probability of the linear predictor plus epsilon being greater than 0, which amounts to saying the probability of epsilon being greater than negative to linear predictor. And now I take advantage of one of the properties of the logistic distribution, and that is that the logistic distribution is a symmetrical distribution, which means that the probability that epsilon is greater than negative eta is exactly the same as the probability of epsilon being less than eta. That's what I've done here. Less than or equal than eta. And then here I substituted this is a cumulative probability. And cumulative probability is the probability of scoring some value or something less. And I can get to that probability by way of the cumulative distribution function, which in this case is the cumulative distribution function for the logistic distribution, the standard logistic distribution, which happens to be e raised to the power eta over 1 plus e raised to the power eta. And when I'm lazy, I just write that as big F over eta. Now, this is what that thing looks like. So here's the linear predictor, here's our probability scale, and it's an S-shaped distribution with a lower asymptote of 0 and an upper asymptote of 1. That means that you actually technically never do reach exactly 0 or exactly 1 approaching from the lower one. And this is, for my example, what the Logit estimates look like. Big effect, highly significant for being a labor identifier. That's sort of almost tautological, but I put it in there. Big negative effect, relatively big negative effect for ideological distance. Ideological distance is on a 0 to 10 scale, so 0 means you place yourself on the left-right continuum exactly where you place labor. 10 means you place yourself on the opposite side of the ideological spectrum from where you place labor. That's also highly significant. Middle class is barely significant, is negative. Working class is not significant. The baseline for class here is people without a class identification. And then we have constants. Well, this is the Logit specification. There are alternatives, but I will not talk much about them because the Logit specification is one that we can carry with us very easily to ordinal dependent variables and polytomous dependent variables. But a probit model would say epsilon follows a standard normal distribution, and there's also something known as the complementary log-log-link function, which uses the Godel distribution for epsilon. That would produce something known as the Logit model. They're all it models. Just as an aside, probit is actually the older model, but it was not a particularly helpful model because until relatively recently, it was very difficult to evaluate this probability with a standard normal distribution, because unlike the Logit model, where we use the logistic distribution, it has a nice closed form for the distribution function. The probit doesn't have that. So the probit was, I believe, first proposed in 1934, and then some 10 years later, the Logit was proposed as an alternative, and for the longest time was really the only feasible alternative till algorithms were developed to compute standard normal probabilities. Now, there is one thing that you will see is very different about Logit models compared to hierarchical linear models and regression models. Because in this latent variable model, we have an error term, just as we had in the models we discussed so far. In the models we discussed so far, we would estimate the variance of this error term. But we won't in Logit models. We actually fix the variance. We're fixing the variance of this epsilon to pi squared over 3. And just to add to confusion, pi here doesn't mean the probability. Pi here means the mathematical constant pi, 3.14 lots of digits. Now, why do we do that? The problem is here. This variable is unobserved, which means it doesn't have a scale. And because it doesn't have a scale, these betas don't have scales either. That is to say, I can arbitrarily change the scale of these betas and then offset those changes by changing the scale of y star, and I get invariant results. So to somehow anchor the scale of the betas, I have to anchor the scale of the y star, and I do that by fixing the variance of epsilon. So in a sense, I'm sort of producing a standardized scale for the y star in the Logit model. That's a Logit scale. And the sort of effective range of that Logit scale is really sort of -4 to +4. Past -4, not much happens. In past +4, not much happens either. That's sort of what we use to fix the scale of y, and that is what we can then use to fix the scale of betas. But the point is then that in multi-level extensions of the model, we will never estimate the level 1 variance. That's a big difference to the hierarchical linear model. Now, a little bit about estimation, probably more than you want to know, but I need to say a little bit more because estimation is an issue with these multi-level logic models. And there are some really bad solutions to the estimation that I think you should avoid. So, in the single level model, we actually estimate Logit models based on maximum likelihood, and we take advantage of the fact that y follows a binomial distribution with a probability density, or probability mass function rather, that is pi raised to the power y times 1 minus pi raised to the power 1 minus y. And that then produces a likelihood that is this expression here. This big pi here is a product sign, so that means that we take the expression after it and it's multiplied for successive operations. So you think of this as pi for the first observation raised to the power y1 times 1 minus pi for the first observation raised to the power 1 minus y1 times pi for the second observation raised to the power y2 times 1 minus pi2 raised to the power 1 minus pi2 second. And that is then optimized using Newton graphs. Generally, you will not have any problems with the estimation unless it turns out that one predictor can perfectly account for ones or for zeros, then you get some strange things happening. But usually it's a trivial estimation problem that should go very fast, which is not going to be true once we extend this to a multi-level model. It won't be a trivial estimation problem anymore. Now we have to interpret the results. And this is not so easy as it is with linear models because of this feature. This linear predictor stands in a nonlinear relationship to the probability depending on where you look on the horizontal axis, the effect may be different. So we need to come up with some tricks to perform the interpretation. There's another reason for this, and that other reason is, well, we fixed the scale of the y stars so that we fixed the scale of the betas, but we made a fairly arbitrary assumption to do that. And in fact, if you were to do a probit model, it would be a different scale of the y star, because then the error variance would be equal to 1, and therefore a different scale for the betas. But that doesn't mean that the effect of predictors is really different from a linear, from a probit model to a Logit model. Basically what it means is that we've arbitrarily fixed the scale differently, and that's okay because the betas themselves are in some sense not the thing we want to interpret. We want to interpret ultimately the probability of voting for labor or some function thereof. How do we do that? Well, I'm going to thought there are many different ways, but the ones that generalize easily to multi-level analysis are situations where we can actually do predicted probabilities, and with the Logit model we can also do odds ratios. The predicted probabilities are fairly straightforward because what we end up doing is just using this expression here to calculate. And what we essentially would do is that, of course, we don't know the betas, we just have estimates of them, so we end up having estimated predicted probabilities, but we can compute them this way here. And so here's an example. Consider a working class voter who does not identify with labor and who's at the median ideological distance from labor, which happens to be 1 unit in 2001. Then for that individual, the linear predictor is -1.87, and the predicted probability of voting for labor is 0.13. Now, with these predicted probabilities, the thing to keep in mind is that they depend on everything that's in the model. They depend on every single predictor in the model and also the value of these predictors that I choose. And when we turn to odds ratios, which is where I want to go next, actually we can really start talking about the effects of a predictor in isolation from the effects of all other predictors. Now, what are the odds, first of all, and what is then the odds ratio? The odds are basically equal to the ratio of the probability of scoring 1 over the probability of scoring 0. So it's basically the ratio of pi I over 1 minus pi I, which turns out to be equal to e raised to the power of the linear predictor. Now imagine that in this linear predictor, which is a function of all of the predictors in the model, I take one predictor and change that predictor by delta units. Then I can actually calculate the odds ratio, because I can say, well, originally the predictor was at this value and the odds were this. And now the predictor has been changed to another value that is delta units higher. Now what are the odds? And I can then calculate the odds ratio, assuming that nothing else changes. And the odds ratio then actually turns out to be e raised to the power beta for that predictor times the change we have made to the predictor. And typically, actually, what we do is we set the delta equal to 1, which means we increase the predictor by 1 unit. And then we call this odds ratio the factor change in the odds, which is then just e raised to the power beta. So sometimes that produces very dramatic results. So based on our estimate of the effect of the labor identifier, the odds ratio is, or the factor change in the odds is 71. What does that mean? Well, the odds of voting for labor versus another party are 71 times higher for those who identify with labor than those who don't. That's pretty big of an effect. In general, this odds ratio, or the factor change, is a positive number. If it's equal to 1, that would come about when beta is equal to 0. That means the odds don't change. As you increase the predictor, nothing happens to the odds. If beta is greater than 0, then this odds ratio is going to, the factor change is going to be a number greater than 1. Odds are increasing as x increases. If beta is negative, then this odds ratio, the factor change in odds is a number below 1, between 0 and 1, which means that the odds are decreasing. Does that all sound familiar? Before I throw in the monkey wrench and extend this to multi-level model? Because that's what we actually really have to do with this data. In a sense, I sort of said, well, just pull it all and just estimate an effect. But really, in reality, what we have with this data is that we have actually the information about which constituency a person belongs to. We have some 120 some constituencies. And it is just a priori likely that people in a particular constituency, perhaps because of the legacy of the seat, because of the quality of the candidate, whatnot, have something in common. They might behave fairly similarly in that constituency. And that's what we now need to bring into the picture. And I'm going to do this again in stages because it's hard enough to just do it as a random intercept model. So this notion I now introduce is to say, well, in this linear predictor, let's imagine our linear predictor consists of just a constant and one single predictor. Then, building on what we had before, where did I have it? We say, well, this linear function is then equal to Logit, and we can keep with that idea. So, except we now need to have a Logit that's not just subscripted in I, but since we're also bringing in a constituency, we're adding a J to indicate the constituency to which the voter belongs. So I is the voter, J is its constituency. And then we say, as a level 1 model for the Logit, we have beta 0j plus beta 1j times whatever predictor we're considering here. And that's our level 1 model. And then our level 2 model is going to be actually a model where I just introduce a random effect for the intercept. For the slope on x, I actually end up constraining that to a fixed effect, gamma 1, 0, to keep things simple. But the random intercept, I'm going to model out as an intercept, an effect of variable zj, plus a random component delta 0j, where I assume that that delta 0j is normally distributed with a mean of 0 and a variance of tau 0, 0. There is a similarity here to what we were doing before. I hope you see that. Except the dependent variable is not y, it's the logit in this case. So we can then come up with the following mixed model. Logit ij is an intercept, an effect of zj, an effect of xij, plus this random component delta 0j. And if you then take the inverse of the logit, you can come up with the predicted probability of scoring 1, that is voting for labor, which is that e raised to power gamma 0, 0 plus gamma 0, 1 zj plus gamma 1, 0 xij plus delta 0j over 1 plus e raised to power all of that mess. And this is something you can estimate. Now here's an alternative way using this latent variable stuff. We have yij star equals beta 0j equals beta 1j xij equals epsilon ij. Beta 0j is gamma 0, 0 plus gamma 0, 1 zj plus delta 0j. Beta 1j is gamma 1, 0. The mixed model is yij, I forgot something here, it's yij gamma 0, 0 plus gamma 0, 1 zj plus gamma 1, 0 xij plus delta 0j plus epsilon ij. Epsilon ij, and this is a difference with the hierarchical linear model. Epsilon ij now no longer follows a normal distribution, but a logistic distribution with no variance to be estimated. Delta 0j still follows a normal distribution with mean 0 tau zeros. And this is then an expression for the choice probability, where I've become later instead of writing e raised to power something over 1 plus e raised to power something, I just said. Some function f over all of that. Now, the interclass correlation in this model is a bit different as well as what we saw for the linear model, because in the linear model we said, well, it's tau 0, 0 over tau 0, 0 plus sigma squared. But in this model, we have fixed sigma squared to pi square over 3, and therefore we don't estimate it, and it's a fixed kind of term here. So the interclass correlation is basically the variance in the intercepts over the variance in the intercepts plus pi square over 3. So think about the 2001 British election study data. Now we break them down by constituency. No level 2 covariates at the moment. We have a dummy for identification with labor, then dummies for middle and working class, and here's ideological distance, and then here's this delta 0j. And we want to know to what extent the labor vault varies across districts. And I'll tell you in a moment, I will get to that, I think, today, how I did the estimation in Stata, but here are the results. 127 constituencies with 1,679 individuals. And here are the estimates for labor identifier, ideological distance, total class, working class, constant. Here is the thing that is of interest. This is this variance component, tau 0, which is 0.45 and highly significant. It's of course not a great surprise that the fortunes of labor vary across constituency, but that's what we've modeled here to pick that up. The interclass correlation, then calculated this way, is about 0.12, so we'll say about 12% of the variance in Y star is due to this interclass correlation. It's really 12% of the variance in the latent variable. That's I think important to point out. That's what it is. Now, if we want to extend this model, we can do that. For unit I in context J, we can now also let the slope of x vary randomly, and then that produces this model here, where I've now called this variance covariance matrix T. I mean, I'll go over this fairly quickly because this is really no different, this part at least, of what we have in the hierarchical linear model that we discussed earlier. This part is different. We specified as a logit now, and that was y in the hierarchical linear model. But this part, the level 2 model, is the same. And then the mixed model you get by substituting these two expressions in this expression for the logit, and that leads to this formulation for the logit, or alternatively this formulation for the predicted probability. So we see there familiar things: a constant, an effect of a level 2 covariant, an effect of a level 1 covariant, a cross-level interaction, random effects for the intercept and slope. And the alternative formulation in terms of the latent variables is here. Important here is the fact that when we have this random slope, we actually have heterogeneity. In a single level model, the variance of y star is fixed at pi square over 3, which is constant. But due to causal heterogeneity, the variance in the random intercepted slope model is not fixed. It's equal to tau 0 plus 2 tau 1 xij plus tau 1 xij squared plus pi square over 3. Well, why is this so significant? This is important because the fixed variance assumption is used to fix the scale of the estimators. And if that assumption is wrong, the scale of the estimators may be fixed incorrectly. And I want to dwell on this point a little bit because this is another big difference with the hierarchical linear model. If you have clustering in a linear model, it doesn't mess up your estimates, it messes up your standard errors. But if you have clustering in a logit model, at least of this variety, then it messes up your standard errors, but it also potentially messes up your estimates. So it is actually quite important to take very seriously this possibility of causal heterogeneity. So that's actually an important point, and this is why I am not always so happy with this cluster option in Stata, because people use this cluster option in linear models, and it's fine because it addresses the issue. But Stata then says, well, with the cluster option available for linear models, we'll make it available for any model you want to estimate, including the logit model. And then people think, okay, All I need to do to circumvent the problem of clustering is to ask for cluster corrected standard errors. But that's not true. That solves perhaps the problem with the standard errors, but not the problem with potentially messed up parameter estimates. And that's what I think State and the community there a great disservice by making it so easily available. If this is really the error structure, you have to worry. It's like there's a literature that talks about heteroscedastic logic models. So these heteroscedastic logic models, it's sort of a similar idea because there too, you say the variance of this y star is not constant. It varies from individual to individual, which means effectively that the scale on which the betas are formulated also varies from individual to individual. And if you don't take that into consideration, you get a scale for the betas that may not do justice to any of the observations. That's sort of the issue here as well. Now, you can make this even more general, and you know what? This is where I, for some reason, got an urge to throw in matrices, so I'll skip this. Nobody wants to estimate that matrices. Let's talk about estimation. This is unfortunately, I have to spend some time on this and then we'll call it a day because then I think we'd have to listen to enough of this stuff. The estimation of these models is not trivial. It requires actually special tools, either in the form of numerical integration or simulation. I'm going to focus on numerical integration. And these tools are computer intensive and time consuming. It is not unlikely that you may estimate a multi-level logic model and you may have to run it over a period of an hour, 2 hours. And it may not converge. It used to be really terrible, but it has improved a little bit. I mean, it used to be so terrible that I would never estimate these things using numerical integration, because I could really go on vacation for a week and still not have anything. So it's gotten a little better. Now, why is it so complicated? Well, it's complicated because of these random effects. So, if I knew these random effects, the actual estimation would be relatively simple because I would basically extend this likelihood function that I had before. I just add the complication that I now that I now look at individuals and contexts. But that's all I would have to do. And I don't know these deltas. They're unknown to me. And this means we have to get rid of them. What does that mean? Getting rid of them means integrating them. This is actually the likelihood function we have to evaluate. And if this doesn't look too terrible, this actually is not a single integral. This is as many integrals as I have random effects. So say I have 5 random effects plus a random intercept, then this is a 6-dimensional integral that needs to be evaluated. And computers don't like to do this. This is one of the hardest things for computers to do. And this is where the fundamental problem of estimation of these models, any nonlinear model, really comes in. And this is where there are some solutions out there that you absolutely should not follow. What I will talk about is actually good, but let me just tell you briefly what you should not do. The program MLWin, which is otherwise a fine piece of software, and they recently did improve it a little bit, but they say, well, this is very difficult, let's approximate it. So what they actually do is they come up with an approximate likelihood function, and this is known as the quasi-likelihood, and they optimize that. The problem is, one of the versions of this quasi-likelihood that they have produces estimates that are known to have big biases. Now there's another version where the biases are drastically reduced, but it used to be the case until the recent version that the default that they had in MLWin was the bad estimator, and you would have to ask for the good estimator. For those of you who want to use MLWin, I think the bad estimator is the PQL, what they call PQL, and the good estimator is MQL. But even MQL has some problems still. And so that's actually why I think the consensus in the field is moving towards different estimators. And there seem to be two camps at the moment. One, the Bayesians, who say, well, if you have such a complex integral, we know how to handle that. Do Monte Carlo Markov chain simulation. Throw a Gibbs sampler at it. And that's the one that I will not talk about. And then a camp that has been quite prominently displayed by Sophia Ray-Pesquet and Anders Skroldal, that say, well, we can actually approximate this integral quite well by using something known as adaptive quadrature. And that's what we will talk about. Now, I want to just briefly say a little bit about this without getting too involved. Adaptive quadrature is an approximation method for an integral. And there are many different approximation methods for integrals. One thing you could do is to do rectangular integration. Rectangular integration says, let's just, if you want to get the area under this curve here, because that's what an integral is, the area under the curve, then let's just approximate that by a set of rectangles, and then add the areas of the rectangles together. Now you see in this picture, which I stole from Wikipedia, that when you make the base of the rectangles too wide, these approximations aren't particularly good. So what you end up having to do, if you really want to make this method work, is make the base of these areas really, really tiny. But then you have lots of areas that you need to evaluate, which slows computers down to a screeching halt and makes them completely impractical. So we need something better. Now, Mr. Gauss, who say for the Gauss distribution, actually figured this problem out a long time ago, and said, well, what if we actually, instead of doing this rectangular approximation, take a much smaller set of points, quadrature points, and then use that for the approximation. Now the trick here is that these quadrature points are in fixed locations, and they have fixed weights, and then the integral of some function is equal to the weighted sum of the functions evaluated at the integration points. And what he could show, and what others have shown, is that if you have an integral, that is an integrand that is a polynomial of order 2k minus 1, then you only need k integration points. So say what you're interested in is a cubic function. So k is 2. So 2 times k minus 1 is 3. You have a polynomial of order 3. Then you only need 2 integration points to get the area right. And this is what that looks like with 5 integration points. Here's a normal distribution. We get an area of this normal distribution by picking 5 points, evaluating the weight, the height of these functions at each point, then weighting them by a known weight factor. That is what is known as Gaussian quadrature. And that is what essentially is used to approximate these really complicated integrals in Stata. But you can do better, because as you actually look at this second curve here with a very sharp peak, these integration points here, and again, for this kind of function, their location is fixed and their weights are fixed. Those integration points don't seem to really adequately capture the area under this very peaked curve. They don't even seem to fall under most of the probability mass of that curve. And this is now the idea that the authors of ELECDEM came up with, is to improve this by adapting where the quadrature points are located. So there's a known problem with Gaussian quadrature when you have really peaked curves. And these really peaked curves are unfortunately fairly common in multi-level analysis when you have fairly large clusters. Because when you think about this normal, about the distribution, you basically have a bunch of zeros and ones in their probabilities that you're multiplying. That produces fairly small numbers, and so you get this concentration of stuff that is sort of all very small. So what they do is pick an adaptation where the integration points are chosen under the P, and that's what is illustrated here. And that's what their algorithm does. And from what I've seen in simulation studies, their algorithm actually performs quite well. It is slow. And what is problematic is that there's no consensus on how many integration points you should use. What they themselves say is, well, estimate it with one set of quadrature points, and then increase the number and see if things change, which is not really very helpful advice. There seems to be consensus that you should pick the number of points larger rather than smaller, although if you have several random effects, you may be able to keep the number of integration points relatively low by using something known as spherical quadrature. And I would suggest you do that because it significantly improves performance of the program. So that all you may have to do is go get a cup of coffee before you get your results, rather than waiting for half an hour before you see the results. You can also do empirical base estimates again, which we will talk about tomorrow with interpretation. I just want to show you a little bit about Stata and how you actually estimate these values in Stata. Stata actually offers 3 ways to estimate multi-level logic models. there is first of all Logit, but that handles only random intercept models. Doesn't handle random slope models. There is Logit, which handles random coefficient models more generally, and is actually a pretty good program, except it only handles Logit models, and if you go to ordinal dependent variables or other kinds of dependent variables, it no longer works. And then there is ELECDEM, which also handles random coefficient models, but also can be extended to ordinal dependent variables and multinomial choice models. If all you care about is speed, if you have just a random intercept model, use Logit because it's by far the fastest. Don't use ELECDEM because it's the slowest. Although it has improved considerably. I mean, this is one of the reasons why I was initially thinking of doing this Bayesian, because I hadn't used ELECDEM for a while, and I thought, oh man, I run an example here, people will be looking at the screen for half an hour before they see anything. But actually it's a bit faster than it used to be. In terms of versatility, it's really the best option that is out there outside of going Bayesian. The basic syntax for a random intercept in ELECDEM is that you type ELECDEM dependent variable. If you have predictors, you can stick them there. Then you have to specify the name of the level 2 units. You do that with this parentheses name. Then you have to specify the link function, in this case a Logit, but if you wanted to do a probit, you would just type probit in parentheses. The family, which is the distribution, which is the binomial. And then we have two technical things at the end. The number of integration points, NIP, which has to be set to some number. And I frequently set this pretty high, to 30 or so. Makes it fairly slow. And we adapt to ask for adaptive quadrature. I will give you a quick overview of how that works, including what you can expect for speed. This is just some stuff in the beginning to create variables. This here is the actual commands. So the labor vault as a function of identification with labor, class, left-right distance, and then since I wanted to fit things on 2 lines, is state of continuation indicators. So we'll just run this, and it will take a while. But it used to take really a painfully long time. This I can live with. No, it's not quad core, so it's dual core. But the crazy thing, I think, is that ELECDEM, which is one program that could take advantage of having lots of cores, doesn't. So
Okay.
yeah. So this is the part where it's doing the adaptive quadrature. So it's now done all the integrals, and now it moves on to actually finding the estimates using the multi-graph. So it's not terrible. And Then this is the output that one receives at the end. And I just want to point a little bit, some of the things are the same as what you get in any other command. Number of level 1 units, you get the number of level 2 units. Something that I actually think is a fairly useful thing to look at is this condition number. Pressing something like there's this condition number that you get here. You want that to be relatively small. This is fine. But you don't want it to be like 2,000 or something like that. Because that points to convergence issues. And then you get the estimates of the fixed effects here, and here is the estimate of the variation at the constituency level, 0.45. Now this is a random intercept model. What if I want to do a random slope model and a random intercept at the same time? Then the syntax changes a little bit. Because what you then have to do is specify equations. And this is how that works. You start by generating a constant term, which is just equal to 1. And then you get an equation, I call it the intercept, that is the constant, and then an equation slope, that is for the x you're interested in. And then a lot of the syntax remains the same, except you will have to now here indicate in this EQS the equations, intercept and slope. You have to specify under NRF the number of random effects. Well, there are 2, so we want to estimate 2. And if you want to do a spherical quadrature, you can do that with this IP parentheses M option. And if you want to suppress the covariance, so we're back to this thing here, you can do that by saying no call as an option. So I'll show you how that works, and then I think we'll call it a day. So say I'm interested in whether labor ID, this identification with the Labor Party, whether the effect of that plays out differently in constituencies. You'll be disappointed in the results, but the answer is no. But then here is the specification, except this number of random effects too. Need to specify. There's one little trick. If you want to do this IPM condition, this can maximally be 15 for the number of integration points. So let's run that. Now this will be a lot slower. Oops. What is going on here? Variable int not found. No, because I didn't create it. Also variable found. Let's try it again. Oops. Well, this is slowness due to my infinity, so there is nothing to do with the program. Let me see, equation is slow, into slow. Why is it in system and cannot find integer?
So there's another intro.
Another inter that I created. Definitely a trick. Now I call this integer C.
Is that on the first line too?
Is that supposed to be an interaction?
Left, right.
Well, I don't want to do that.
It's late, we'll get there.
It may be very late, but fine. This be slow, so we can do something for ourselves. We need to get used to it.
How is this different than LME4 in R?
Well, LME4 in R is also adaptive quadrature, I think. Or in any case, Gaussian quadrature. But I am not sure about their implementation of the quadrature. So I have some concerns about LME4 for that reason. I mean, an adaptive quadrature is actually better than Gaussian quadrature, so go for the adaptive quadrature. I am generally someone who uses R a lot, but I have not been all that impressed with the multi-level stuff in R, so I have not used it a lot here. So. Although I think it's faster than this.
Yeah.
For sure. It's partially a problem of how they coded this up. They coded it sort of as an add-on to Stata, which makes it a lot slower to interpret the code. And then they improved some of that, but it's still not perfect. If you use the Stata internal code as in the XT Logit, it's also much faster than this.
The XT Logit, it is faster than this, but it can take some time as well.
Yeah, I know. But it used to be, at some point this was so slow that it was faster to run a Monte Carlo simulator for 1 million iterations than this. Then I thought, well, what's the point? But then it has improved. So it's done integrating, and now it's going to produce some optimization results, which will also be visible. And may give some interesting warnings along the line that I can discuss. Just have to remember, one of these runs I did with lots of warnings. Yep, here's one. Back up. Not too worried, just early in the process. Backed up means going from one step to the next, and you can see it, the likelihood didn't improve. It should improve from one step to the next, but it stayed the same. So it had to do something to fix that, and it figured it out by the second iteration. So when you get these messages on the last iteration, then you worry. But if you get them on the early iterations, ignore them. And then the variety condition number here is not great, 282, but I've seen far worse than that. Here are the fixed effects estimates, and then here is the correlation matrix, which I think, so this, actually, this is something to be aware of. So, Stato, when it grants something, it always puts the constant last. So the last variance component is the constant. But the way I specify the equations, I specify the equation for the constant first. So this is actually the variance of the constant, and this is the variance in the effect of lap ID. And this is the covariance, and here's the correlation, which is pretty high, but it's not a corner solution, I would say. It's far from -1. Now, if you look at this, though, and this is sort of a bad way to judge significance of variance components, but it gives you as a heuristic, it's not bad. This is smaller than the standard error. Seems to suggest there's no significant variation in the intercept. This is barely larger than the standard error. It doesn't bode well for there being some significant variation in the slope. This is smaller than the standard deviation, so it appears that all of these variance components, they look very close to insignificant. Part of why the intercept variation is so low is that I actually included in here a attribute of the constituency, which was the overall vote share of labor in that constituency in 2001. If you see this, you may want to test whether you really need these variance components, and that's then the last thing I will do, and then I really will let you go. Want to do a likelihood ratio test, where the constraint model is basically a model that sets all of these components equal to 0, which is essentially the same as just estimating a standard logic model. So, what I'm going to do is store the estimates the way I did before. And now I will just estimate a Logit model. What are the predictors again? Logit, lap vote, lap 01, lap ID, middle working, LR list. And now I want to do a likelihood ratio test. So I do LR test, call up the results from the unconstrained model, and this is what I get. Status says, forget it. You use two different estimation commands. I'm not going to do the test, but it's easy to trick it into doing it anyways. You just say LR test full, and then
LR.
LR test full, and then force. And Stata will do the test for you, and you see likelihood ratio test statistic with 3 degrees of freedom is 2.18. That's pretty low. This is the conservative estimate of the p-value, but even if you were to cut that in half, you would still get a p-value that is well above 0.10 or 0.05, whatever cutoff you want to use. So what this suggests is you can actually now estimate a model without these various components, and you will be in pretty good shape. But that's the difference. We ended up there after we went through the proper analysis, as opposed to starting there and hoping that it was the proper analysis. So that's a big difference. And then, of course, comes the task of interpreting. With that task we will get to in the morning. Then I will also, but at a much more practical level, talk about ordered logic models and multinomial logic models. And then learn more about multinomial analysis. Hopefully you did before coming. So, we'll see you tomorrow.